So Eurodrive motor brakes are incredibly reliable, but troubleshooting them by trial and error is a guaranteed way to destroy expensive rectifiers and coils. When a brake is miswired, or when the rectifier fails to release the mechanical assembly, the motor attempts to drive straight through a locked brake. The friction disc turns to ash within seconds, and the resulting current spike violently pops the control module. To prevent that, we are going to walk through a strict 3-minute testing procedure and break down the core 3-wire logic that keeps these components from burning up. Before we start, you need 3 things: a digital multimeter to read ohms, your personal protective equipment, and standard lockout-tagout gear. Replacing guesswork with a precise diagnostic routine will save you thousands of dollars in ruined electrical components and hours of mechanical downtime. Step 1 is always safety. Disconnect all high-voltage supply power to the motor and apply your lockout-tagout devices. SE brakes are electrically released, but mechanically engaged by heavy springs. When power is lost, the brake immediately clamps down. This creates a severe mechanical drop hazard. If you are troubleshooting a motor that holds a suspended load and the brake is manually released or loses power, gravity immediately takes over. You must mechanically block or safely lower any loads before you even open the electrical conduit box. Failing to secure the machinery before probing the electrical system exposes you and your team to fatal crushing accidents. To understand how the brake operates, we have to look at its dual coil logic. Pulling heavy springs off a friction disc requires a massive surge of magnetic force, the kick, but holding those springs open requires very little current, the float. The SCW system accomplishes this using a 3-wire design connected to 2 separate coils: the low-resistance accelerator coil for the kick and the high-resistance holding coil for the float. The white wire acts as the common center tap shared between both coils. The red wire connects directly to the low-resistance accelerator coil for the high-current kick. The blue wire connects to the high-resistance holding coil, keeping the brake open without excessive heat. You will encounter different rectifiers in the field, like conduit-mounted BGE blocks or cabinet-mounted BMK modules, and their terminal numbers will change, but this red, white, and blue logic remains constant. Knowing how these wires divide the high and low resistance circuits gives you the exact blueprint needed to test the health of the brake module. With power locked out, completely disconnect the red, white, and blue wires from the rectifier terminals. Set your digital multimeter to measure resistance in ohms. For your first measurement, probe the red and white wires to isolate the accelerator coil. This reading should show a low resistance value, typically about 25% of the total resistance. Next, move your probes to the white and blue wires to measure the holding coil. Because this coil restricts current, your reading here should be significantly higher, roughly 75% of the total resistance. Finally, place your probes on the red and blue wires to measure the entire circuit. Your final reading across the red and blue wires must exactly equal the sum of your first 2 measurements. If any of these pairs show 0 ohms, indicating a short circuit, or an open line indicating a break, or if the math simply doesn't add up, the coil has failed. This straightforward arithmetic tells you immediately if the internal windings are destroyed, giving you a definitive diagnosis with ever-touching live voltage. This brings us to the golden rule of SEW brake maintenance. If your test proves the brake coil has failed, you must replace the rectifier at the exact same time. A shorted coil draws massive current and heavily damages the internal switching circuitry of the rectifier. Wiring a brand new coil to that damaged rectifier will instantly fry your new component the moment you turn the power on. Wiring sequence is equally critical. If you accidentally swap the red and blue wires during reassembly, the rectifier sends its initial high power kick to the high resistance holding coil. The magnetic force will be too weak to pull the springs back, the brake won't release, and the motor will turn the locked friction disc into ash. During installation, never apply raw alternating current directly to the DC coil wires. If controlling the motor with an inverter, remove any factory jumper wires running from the terminal block to the brake rectifier. This ensures the brake receives a constant, independent voltage supply. Treating the brake coil and control module as a single paired system is the only way to stop replacing and instantly destroying expensive hardware. You now have the correct sequence to safely and decisively evaluate the electrical health of an SEW brake without risking a meltdown. However, if your resistance numbers are perfect and the brake clicks open properly, but the housing is still overheating while running, you are dealing with mechanical drag. As the friction disc wears down over time, the clearance increases. You will need to check the physical air gap with feeler gauges and adjust the hex nuts to ensure the disc isn't rubbing against the armature plate. To verify your specific measurements, go to the SEW Eurodrive website's technical notes section and download the brake coil resistance data table. That document provides the exact numerical specs for every motor size and voltage range. By combining accurate data tables with a disciplined 3-wire testing procedure, you turn a hazardous, high-voltage guessing game into a calculated and repeatable diagnostic routine.